Churchill. Can you hear me? Hello? Can you hear me?
Yes, sir.
Okay,
Yes, sir.
can you see my screen? No.
Yes, sir.
Yes, sir. Yes, sir.
Don't see my screen. Okay, let me see that.
So we can see.
Can you see the screen?
Yes, sir. We can see.
Can you see it? Hello?
Yes, sir.
Yes, sir. It's
Huh?
visible. It's visible, sir.
Visible? Okay, fine. I don't know what happened to that. Wait a minute. Hello, let me start. Okay. First of all, give me some assignment to particular students. Okay, wait a minute. ये कहाँ क्या हो रहा है? ये सब ये है. I want to give assignment to particular students, so they will send me by within a week and then I'll post it. So let me tell you that. What is that? First of all, one, the first countable space. Next semester you will start doing projects so that you need to learn how to write properly. So here you will give definition, starting with local base, definition, first countable, and two layers. That's sequential, characterization, of closure point, and continuity. Okay. Also, you should give example. Example or example, give an example of a non-first countable space. And show that, and example of failing this thing. Okay, this who will do it? This is horse will do it. Okay, this horse person will do it. First control. Now I'm coming to this. True. Okay. Second countable space. Good. But before that, you need to start with base for a topology. Base for a topology, definition you click. And then you will see given when necessary and sufficient condition. When B gives a topology, you know what I said, because the topology on X. That means the topology generated by this. Okay. And then you'll do second countable space. And definition. Then you will do this result. It implies separability. But counter example, separable space need not be second countable. That you do not need to, that somebody else do it, but you can do it if you want. Second thing, the metric space is second countable if and only if it is separable. This, I think he is present. Sarthak will do it. This will do it. Second countable space. Okay. Now I'm giving particularly the third surgeon free line. Origin free line often also is defined, written the notation is RL, that is lower limit topology. L stands for lower limit topology. Okay, so that first you will define the topology. Two, of course, you will show RL is first countable and separable. Three, RL, this is important, is not second countable. Okay, make sure you do it. I'm giving you one more problem here. Let me see that whether I can find it. It's in the wheel somewhere. Yes. Which it is, I'm taking from Willard this problem. If you want to see, it's a problem in Willard. page 36. 4A2, page 36. Which intervals on the real line are open in order. Look, in R, the usual topology we know an interval will be open if and only it is an open interval. But here, which intervals? Okay, so that people who submitted the assignment I am giving them, Sanjuwala will do it. Okay. So that by next Monday you should submit. Okay. That is the first countable, basically second countable, and surgeon feline. Okay. Right. Make sure that you do it. And you people do it, because if you are going to look for recommendation from me in future, then you will have to do it. Okay. Now, what I want to teach. Okay, first thing, let's not forget tomorrow I won't take any class. Tomorrow is 18th January. No class. So I will take little bit extra time here, and on the Friday I will take. Okay. Now the thing is that I want to talk about two things, Moore plane. That I will do little later on. But before that, I want to talk about subspaces. Okay. Now look here. Basically, it is a broader thing broader aspect is that how to create, basically the philosophy is how to create new spaces, new topological spaces from the old ones. This is the philosophy. Okay, this is very important. Okay, so first here in between, here you have the subspaces, quotient space. This is very important in algebraic topology. Quotient spaces and product spaces. These three are the main thing: the subspaces, quotient spaces, product spaces. That I will do one by one. The first I want to talk about this one. Moore plane, you should remind me that if I forget that. So that subspaces. Okay, so you are starting with extra in a topological space. Let me tell you that in Willard there is a chapter on that. But since I have given you Ali branches, I am just because it's a book for analysis, they have given only short thing. Now here, let me tell you that example in Ali Francis Birkinshaw, it is example 8.7, page 58. The subspace topology. Now look, suppose, yes, what do we mean by that? Phi, non-empty set, is a subset of X. Now I want to have a topology 1Y. Look, Y is a set I can have many topology, like indiscrete topology, discrete topology, but that is not the question. Question is, I want to have a topology on Y relevant to that, naturally related to tau. If I can find such a topology, that will be given, that will use the notation tau Y, that will call subspace topology. Okay. Or some people call it relative topology. More precisely, relative topology, subspace topology induced by, given by tau. Okay. And in that case, this is called a subspace, whole thing. Subspace of this, of X. Now, let's say how to define naturally. Here we have the example of the simplest example, how to do this. Okay. Look, when you have this thing R with usual topology, that means this is a metric giving is this topology. But if you want to consider on this, same metric you are considering, but what will be your topology here? Look, here what will be the open sets here? Of course, open sets will be a subset of this. But have you thought of that? Here on open set, here, open set in 0, 1. Suppose U is an open set. It can be written as this. Where V is open in like, look, this is open in this. That means with the, of course, with this metric, actually here it is restricted to this. This you can write as, I can write got it. This will give you this, but this is open in R. That you can always check that. But that means what? If I go for a subset, if I want to have the open set with respect to this, basically I want to have the open sets here, but only that part which is contained, obviously, because my ambient space.
So shouldn't the
intersection
will be
that part of the open set I will consider, which is there. That's the way we naturally define the topology. You can check that this will give you a topology. Okay, that's the thing, intersection. Okay, so that what, how to define that?
Sir, the last statement.
What are you saying? Hello?
Sir, the last line where we are taking the intersection with R.
I can't hear you. Hello?
Hello, sir. Am I audible, sir?
Hello? Batao.
Sir, R should be the in the R should be,
Sir, the intersection should be with closed interval 0, 1.
0, 1, yeah, yes, sir.
I'm 0 to half to Leah. So minus half.
Sir,
what would be the intersection?
Sir, you have written V intersection R. In place of R, there should be 0, 1. Close interval 0, 1.
Oh, sorry. Yes, you're right. Yes. Yes, you are right. Yes. Okay. So this will be our idea. Now, so if you have this, I'm going to write it properly. Yes. I'm sorry that I didn't realize that. I was thinking somewhere here you were telling me. Okay. Now, suppose you have this. Okay. Now, what will be the topology? That means here, look, tau y should be all those collections V intersection y. I have written here y such that V belongs to tau. That will be a topology because whatever the conditions of topology I have given you, that will be automatically satisfied by the plane operations of set theory. Only thing all the time you will be carrying this luggage V intersection y. Okay, right. That means all the open sets you take x, but only that part which is contained in y, that you'll have to consider. So that here so definition, let X tau be a topological space. On empty set, we do not bother to define topology. I mean that doesn't make sense. Okay, be a topological space, and this is a non-empty subset of X. Let tau y equal to this. This is all basically tau open sets in X. This means open sets in X. Let then tau y is a topology. You should check is a topology on y, and y tau y is called subspace of X tau. But often we just write y is a subspace of X. Just right. It is understood. Here you have a topology tau, and then if you have topology tau, here the topology is tau y, this topology. Okay. Now let me see that. So that open set you have defined this way. So some exercise I am giving you that is very easy to check. That results I can write. One. First, look, let this, I think it's a C subset of Y. You are having a topological space. Then C is closed in Y tau Y if and only if, like open set, the result, there exists a closed set C prime in X tau such that C equal to C prime intersection Y. Like here open, you take closed set. If and only if there exists a closed set. It has to be, it must be of this form. Okay, so you can prove it by using just the definition. Okay, right? Okay, so I am not proving it. You should prove it. It is in one line or rather two lines. If you write big, then it is two lines. If you write small, it is in one line. Okay. When you allow somebody to copy in your exam, in class exam, then you write big. Okay. If you don't want to allow your friend to copy, then you write small. Okay. Right. So that depends on you. Okay. I have experience of that. Funny thing is that who copied, he got more points. And the other guy cried. I showed him and he got. Now you understand how you get the benefit out of helping your so-called friends. Okay, right. So that Now closed set, open set, closed set, you have got it. Okay. Now the thing is that you can also prove this result. I should give you this thing. Look, when you in R you're taking and why you are taking this, but this is open here, but this is not open here. That's a bit of anomaly. Similarly, you can construct example for closed sets, but here you can see that let x tau is a small result but very important. X tau be a topological space and y be a non-empty, of course, non-empty open set, non-empty open set in X. That is, look, this thing doesn't happen here. If you take this, then it will come this. That is also open in R. Okay. So here the result is y belongs to tau. Self. Then let u subset of y. Then u is open in y, tau y, if and all if u is open in x tau. That is, u belongs to tau y if and only if u belongs to tau. You can see here the example. Here open set, there is no anomaly. It will be open here in the subspace topology if and only if open here. But here it is not true. But here the closed sets will play that role. Here a subset will be closed if and only if it is closed here. Okay. So that so similarly you can write X tau be a topological space and then let u be subset of this. And here let X tau be a topological space and y be a non-empty closed set in X tau. That is, x minus y belongs to tau. Let C subset of y. Yes, C may be empty also, subset of y. Then C is closed in y tau y if and only if C is closed in X tau. If you don't need to mug up, need to memorize the things. If you think what will be the result, you just go what the example I was giving in the R and close interval 0, 1, open interval 0, 1, then it's. So this you can prove. This is proof set very straight. Okay, how we will get the closed set open set. Okay. Now the thing is, now look, you have X tau and you have a non-empty subset of this. So you have y tau y. Now suppose you take a subset of Now look, I can consider the closure of A in Y top. I can also consider the closure of A in X top. Look, they are different usually. Okay, the closure of A, unless Y is closed and A is closed, usually they are different. Okay, so what will be the relation between this? The closure of A, that's why when we have subspace and that, eventually we write this notation. We just don't write A bar because that will be, it won't say anything whether you are taking closure of A in Y or closure of A in X. Then we write this notation. Here the notation is closure of A in Y, and the notation is closure of A in X. Okay, right? And what should be your result here? You can prove that this will be equal to what should be closure of X A, that part. This is the result. Exercise. The closure of A in Y will be just a part of the closure of A in X, which is in Y. But what about the interior things? I didn't talk about the interior things. For interior, let us see whether it is true or not. Okay, right? So it is exercise. That means result. Let me write it. So I'm giving you this. Somebody else later on will have to do this assignment. So result is this. Let X tau be a topological space at Y be a non-empty subset of X. Let A subset of Y. Then it has to be, because I'm to closure of A in Y equal to closure of X, A intersection. Okay, that you should be able to prove it. Well, for interior, let us see. If I put interior, then it should be interior A in Y equal to interior X A intersection Y, right? Let us see. Now, in this, take Y equal to Q. You should understand one thing. In any topological space, if I take, it will be always X. This, because it's itself open, but in this thing. Okay, if you take Y equal to Q, and A also take you A equal to Q. Okay. Now look, interior Y in it, so interior. Interior YQ, both are same, so it will be Q. But interior X ZAR. Look, this is what? This is empty site. This is empty. So with this empty, it will come intersection. Okay, it will be empty. So this will be empty. On this side, it will be Q. So this is not true. But one way subset will be that there. That means this will be always true. I think this we can prove. This will be this. This you should check. Okay, that because what I have got here. Okay, so that for interior we do not have this result. Interior only we have this thing. So be careful about interior. Interior makes problems. Closer behaves much better. So that often you should be careful with the interiors. Okay, so this you got. Okay, closer it is true. For interior it need not be true. Okay, here the simplest example is this I have taken. Okay, so that all these results you should prove. That will be good enough for subspace. If you want to have more information of subspace, let me tell you that where from Willard you can read that. Let me wait a minute. There is a chapter that wait a minute. New spaces from old. Chapter 3 in Willard. That I want to do it now. Stephen Willard. Okay. Subspace you have 41. Page 41. Let me see that. Okay. So that all the results particularly you should get in 42 theorem 6.3. Okay. Right. And look at example 6.4 is giving example that is the interior thing that I gave actually 6.4. Okay, right. Okay. So this is subspace. Now how the subspaces behave with respect to the parent space, that is called, we call ambient space also. That means parent space so parent space, or this is X tau, this is called parent space, and this is subspace. Of course, when you write it, we assume, of course, Y is non-empty. Or whole space called ambient space, the word. Okay. Now look, like suppose I have first countable here. Will it be first countable? That means at each point here also we'll have a local base, the local countable base. If it is second countable, will it be second countable? Yes, that is true. So that let me write it. That is the proof is very straight. But look, base, when you're talking about base, suppose this is a base for x. A base for x. All you'll have to see, I'm taking global base, second counter. Base for x, all you'll have to see that, then this thing. This is notation. This means it will be a base for y. If you have countable here, of course it will be countable. You are taking the same thing, only each time you are taking intersection with it. So this will be base. Similarly, look. Suppose at a point you are taking the base bx, local base at x. Okay, local base at x. Then what will be the local base if x is for x in x, and when x is in y? Of course, you'll have to think of that because outside y I don't need to bother about. Then look, this one, like here. So basically I am giving you the proof. So this will be a local base, whether it is countable or not. It will be local base at x in y tau y. Okay, if this is a local base at x in x tau. Okay, so if it is, if you can pick up a countable base here, so it will be countable here. So that subspace of a first countable space is first countable, subspace of a second countable space is second countable. So I can write this result. Okay. So then let me write this result. Let x tau be a topological space and if x tau is first countable, so is y tau y. People usually write in the bracket respectively second countable. I am writing separately. If x tau is first countable means it has got a countable local base at each point. If x tau is second countable, I'm writing this second countable, so is y tau y. Well, I have told you first countable, second countable, and also these are called the countable axioms. Countability properties of a topological space or countable axiom, because everything countable. What about separability? That is the thing. That means if x tau is separable, whether it will be separable or not. Okay. That's a big issue. Okay. Right. That's why I have given you that thing. Every second countable space is separable. For a metric space, it is separable if and only if second countable. Now look, for metric space, how will do that? So let me give the result for the separability for the metric space. Okay. Let me write this. Let xt be a metric space. And okay. If xt is separable, so is this restricted metric gy. Okay. It doesn't matter any subset. Okay, but then here is an issue at that. You say, how I link with this subspace? Because right now, just until now, I have talked about only x tau tau y. I have not talked about this. This result is true. Okay. But before that, I need to fix one thing. What is that? How tau y is related to, now look, here it will give you a topology tau d. Listen to me very carefully. Here it will give you a topology tau dy. But here, if you go for subspace topology, then it will be this by my notation, tau dy. Now look, apparently I am getting two topologies on y. It is this topology induced by dy, the metric restricted to y. And here I am having the topology subspace topology. So these two. If I know these two are same, that means look y. if I can push it inside the bracket, here it is inside the bracket, here outside the bracket, then it is easy to prove. Why? Look, if you use the previous statement, that I'm coming again, but I am right now, I can tell you briefly. If X is separable, then it is second countable. Subspace of a second countable space is second countable, but any second countable metric space is separable, so it will be separable. Okay, so that, but this thing I need to prove. Okay, so this is true for metric space. For GAN space, it need not be true. That I want to give you example. So that first thing, so this thing I am leaving in exercise, but I have already explained that. Now, how will I mean, I can tell you that how to prove it. Okay. So you are having a metric space xt. Okay, and of course you are having this. On this you have, this is metric, same metric D restricted to 1. Metric D restricted to 1. So here you are getting D, it is coming tau D. And here, this, after that you are getting D tau D, okay, this. And here you are getting dy, and this you are getting, okay, tau dy. And here look, you are getting subspace topology. That will be this notation, because tau you have, I am putting this here, topology is tau D, because topology induced by, generated by the metric D, so it will be this. So this way you are coming. D, first you are restricting metric D to Y, and then you are taking topology. Here you are doing the other way. First you are taking the topology induced by D, and then you are taking the subspace topology. And you will prefer a situation, they should be equal. That means whether I go this way or this way, I should reach the same thing. Yes, this is true. This is true. But the thing is that how to prove it? Only way you can prove it, you take an open set here. You know it is coming from the metric D. So your open sets will be generated by the open balls. And then you'll have to show it is here. And then you take here, you show it here. Okay. So this is the thing. That means diagram commutes. This diagram commutes. You will reach it. Whether you come this way or this way, you will reach the same destination. Okay. So let me write it. I'm not erasing this one, the diagrams, the result. Let xt be a metric space and then this thing. I have explained the notation tau d y equal to look here. Basically, in mathematics, this is very important. Whether when you can do it logically to change the place of the operation. So there's some operations commute. You look here, I have an operation in bracket and the subscript y. They're commuting. I can y can be pushed inside. That means bracket and this operation subscript, they're commuting. So that's the good. It doesn't matter whether if you are a forgetful person, it doesn't matter whether if you wonder that whether I put the y inside or outside, it will be the same thing. Okay, that's the thing. I think major theory you're doing later on we'll see that. What is Lebesgue's dominated convergence theorem or monotone convergence? Basically, but suppose you have, when you have the integral, you'll have this with respect to something major, the limit n tends to infinity, integral. Now the question is that when I can do it. Of course, I assume this function exists. That means here integral and limit, the two operations when they commute. That's a big thing in the measure theory. In fact, measure theory rests on this idea. When it is possible. When it is, of course, if you just force in any situation, then you will end up with a situation like 0 equal to 1. So you need some hypothesis on that. It's not always will be true, but under certain condition, we'd like to have a situation like this. Similar thing I am having here. Okay, right? So you got this. Now with this, you can prove. Okay, right? Now this thing, this you can prove. Let xt be a metric space. I'm writing separately, but I could add there also. Be a metric space. Be a separable metric space. You can write separable metric space. Be a separable metric space. And then y is also separable. Look, the previous result, the metric space is separable if and only to second countable. So xt, what will be the proof? Xt is separable. Okay, implies metric space is second countable. That's x tau d. Separable metric space is second countable. This same topology. Separability is actually a topological concept. Implies, since it is coming from a metric, is second countable. You should understand that since X is a metric space, you should write since X is a metric space. Implies X, sorry. But every subspace of a second countable space is second countable. So Y tau d Y is separable. Okay. X is separable if and only if this is separable. This is if and only if. The same thing. Okay. But since a metric space, it will be second countable. So this will be second countable. That I have given the result. As I told you how to prove it separable. But since this is equal to this implies y tau dy is separable. It is okay, right? That means for metric space, it's very nice. That I told you all the time that metric space behaves very nicely. Okay, so that any subspace of a metric space, I have not put any restriction. Any subspace of a metric space is separable. But in the people put it. Look, how will you do that? At your level, the best result you can have it for the separability. Let me write this. And let me give the proof of that. Let X tau be a topological space, separable space basically. Separable space means separable topological space. P is separable space. That means that, of course, it's a topological space. And Y be a non-empty open set. This is very important. Open subset of X. Then basically we say that every open subspace of a separable space, every open subspace of a separable space is separable. Okay, I'm going to give you the proof on that. Not the details, you should work out where I am going to use the open. And I will give you that's the Moore plane I want to talk about. If I didn't have open, it did not be true. Look, how will you do that? Okay, and where you need openness. So proof. So here, be careful. I'm having separability density so that I should have the closure reducing this. So let T be a countable tensate in X star. That is, what are you saying? That is closure of T in X equal to X. Okay, right. Now take this, let consider D1. Let I think you can take D1. D1 equal to D intersection Y. Now look, this is given open and D is dense, non-empty open set. So this is not equal to phi. I told you last time, say it will be dense if and only every non-empty open set intersects that set. Since Y is open in X. Okay. Now since D is countable, D1 is countable. Okay. All you need to check closure of, this is a subset of Y and this is non-empty. Closure of D1 in Y is Y. So it will be separable. So this you will have to check that. I have given you. The most important thing is that this. There is no guarantee if you start with an arbitrary topological space, this may be empty. This may be empty. See, but if you can ensure this is, look, it is a sufficient condition. Openness is guarantees that it will be non-empty. But you don't need all the time open sets on that. If somehow if you can guarantee this is non-empty, then it will work. You can check that. Okay. Now thing is that if it's not open, then it need not be true. Okay. So that let me give that counter example. That how do you do that? How? Let me write that. So that I want to just explain that. The Moore plane. What is Moore plane? It is given in Willard. It's a nice counter example. What is Moore plane? कहाँ से आ गया भाई? Moore plane. Well, Moore was a great topologist on that. I think he is in my family tree also. RL move, right? Okay. What is Moore plane? Okay, now look, Moore plane, we're taking only the upper half. That means in R square, we're taking Moore plane. If you take, call it M, we're taking this X, Y, Y. So, बहुत ही problem. Y greater than equal to 0. That is upper half plane, including the x-axis you are taking. Okay. I can write the topology, I will take it, but now I have to give a topology. How to give this topology? Look, you can have the, right now you got the usual topology, usual subspace topology, you could take that. Usual subspace topology. That means topology induced by the topology on R square. So that is called the usual subspace topology. But I am not taking usual subspace topology because look, R square with usual topology is separable metric space. So this will be separable. So AM with usual topology, that means induced by the usual distance. Usual topology means metric is the topology induced by the usual metric. This will be separable. So no, just now what I proved. So that is no problem. Okay. But the thing is that I want to change the topology here. How do I change the topology here? Okay. Look, I'm not going to change. Basically, I do it define point wise. But suppose you have a point here, they call it neighborhood system at a point. Then as usual, you take it to consider topology if you have the ball entirely contained inside. Okay, that thing. That means here you are not changing. But here at this point, look, but each point on this, here you see, on x-axis. Here, if you take the subspace topology, actually it will come, its ball will be, look here, ball will be disk actually, will be half of this part. This part will be there, only half of this. But I am not taking that. So I will write, what I am going to do it, here the disk, open disk, but I will take such a way that it touches the point. So that those will be the neighborhoods of actually the points on the x-axis, touch. Okay, right. So that if you have a point, so that how will I define this? This gives you a topology that you can check that. Actually, this will be the base actually. The ball, the disk you are taking, but on the point x-axis, your disk is different. And that will be a base for a topology. Okay, so that, let me tell you that. How do you write down that? Willard has talked extensively about the neighborhood system at points, so he has talked about that. Since I want to avoid it, so I am just giving straight on that how to do that. Okay. Search it. What is that search it? Okay. Here पे किया. Look here. So M is this thing. X, Y, Y. It is not coming here. Search किया क्यों पता नहीं. Y greater than equal to 0. Okay. Now V is a subset of M. I will call V open and suppose 0 V intersection x-axis is empty. Okay. Well, okay, I don't need that. Call V open. I can giving the straight opposite. I could take subspace. There is a base. Call V open in some topology that I am defining. If 1 xy belongs to phi and y greater than 0. Okay, right? And there exists r greater than 0 such that, like disk actually, open disk, sorry, p यहाँ पे कुछ xy लिया, so I'll have to write this way. P, here the point is xy, r contained in phi. Okay, right, open disk. Okay, entirely inside phi. Phi is this subset. 2 if xy belongs to phi, it may not be there, and y equal to 0. Okay, y equal to 0. Okay, then look, what I'm going to do it. How do I don't know how will I write it. That basically this is your point x0. You are taking this. Okay. So I don't know how to write it. This kind of disk I need. Okay, right? There exists. We can write this thing. Let me see. There exists r greater than 0 such that px0 r, this is here, this with this. You should tell me that whether I am writing correct. Because it will be outside this. I'm taking disk plus this. It is contained in V. Got it? Huh? Call V open. If you have this point, we need not have that point. That only need to consider this thing. But if it has a point from the x-axis, then you will have this. Okay, right? Got it? This will give you a topology. You can check, because what are you can check as the through basis, because this kind of disk, that usual disk and this kind of this disk, if you include that will give you a base for a topology. That's the topology I am considering. Okay, xy belongs to be y greater than 0, then the usual thing. And if you have this, then you have a disk, this like entirely open disk, but corresponding this also is this part of this. This has to be. So this will give you a topology. Now that you should, and with this topology, this is called a Moore plane. Sorry, it's called a Moore plane because it's a part of the plane, and you are giving a topology, so it's called Moore plane. Okay, right? Got it? It's fine. Make sure that you do it. But if you can look at Wheeler, the problem is that he did through neighborhood systems, but still it's not going to be a problem. You can check that 4B, page 36. I'm just giving the reference if you want. We can do, actually we can define topology in many different ways, Another way is that at each point you define neighborhood systems. So that he exactly did. In fact, in first two chapters, supposedly we spent a lot of time how to define a topology in different ways. Okay, so but I have given straight what I have taught until now. Okay, I'm just declaring open sets. I'm declaring straight open sets. Now, Moore plane is separable. You can easily check what will take. This set D. Look, I will take this. But why? Same thing, like similar to real plane r square. Okay, so that only thing you are taking the thing, only that part xy rational to y greater than equal to 0. So this is countable. And you should check that this is dense. Sorry, this we have that. So it is dense. So that is separable. But now look here. This point x-axis. What will be the topology on x-axis? That means if you take y equal to this, y equal to this. It is the x-axis we are taking. And what will be the topology here? Now look, I said particularly point. This is open. So each intersection, this is an open set. Open disk, you take open disk here. This is your point, x0. That is intersecting y only at this point. So x0 is M intersection y. Sorry, yes, sorry, M not M. Disk, you call it x0, call it R, whatever a point, something. Here it is y. Oh, that is the notation. I have written something wrong, I think. Let me check that. This should be BYR union x0 intersection x-axis y is this. But this is open. Let me check that what I have written there. This is a point, different point. Okay, this should not be x0. Okay, this should be what point? This is, come on, this should be x here, 0. So it should be some xy. So it should be some xy. Okay. Oh, this y don't do. This is not same y. For y prime, you could write. Okay. For some y prime in R. समझ गया? This should be not 0. Bx0 is this ball is coming. So I have written wrong here. So that's why I got it there. Bxy prime. Okay. So that what I have written here. Here it's fine because I am not R. Got it. But this is open. Because this is actually basic open set. So this is open in M. So this is open. That means every singleton is open here in subspace topology. That means what subspace topology you are getting? Okay, every singleton is open. That means you are getting this discrete, this topology. This is discrete topology. Got it? But it is uncountable. A discrete space is separable if and only if it is countable. So you are getting a discrete space here. So this is discrete and y is uncountable. So this is not separable. Okay, right? So you can check this is not an open subspace of that. Okay, it can't be open because it is, look what happens in that. If it is open, then its complement has to be closed and complement is not closed. Okay, so that this is an example that any subspace, an arbitrary subspace of a separable space need not be in an arbitrary subspace. of a separable space need not be separable. I need only this much. Just try to understand the mood plane. Okay, that will be good enough. And whatever result I have asked you, I left as exercise. Basically, I proved everything, and that you should prove. Okay, you should prove. Okay, so this is the thing.
Sir,
batao.
Sir, in the last slide, sir, you have taken the defined metric with respect to y greater than 0. And second condition, you have taken with respect to that, sir. Last slide, sir.
This one?
No, sir, last one. Before this.
That is the previous page, I think.
Yes, sir. Yes, sir. In that, sir,
X here, the x-axis is this will be the x also. This way, the simple school geometry. The first coordinate will be x actually, na?
Yes, sir.
First coordinate will be x. That I have taken. I don't know much of school geometry, but this is x coordinate x0, so this will be also x coordinate. That's the way the disc is coming. Okay, you go with that. Okay, that's why I've taken this x and y prime, but this y coordinate will be different because here I am saying y equal to 0. I'm to use the different notation. Okay, basically idea is that you will have an open disk which should touch this. Okay, but when you touch it, I can take this way. That is okay. I do not know. Can you have any other disk touching this way without this x it being x coordinate? I do not think you can have it. Okay, but even then it doesn't make a difference. You can have another way than that if you have that situation. But I think you will have this same thing. Okay, right? So that this thing, mood plane example, even if you go for some other thing like algebraic topology and that, this is a good thing. You should see that mood plane. So that study mood plane. Okay, just see that. Okay, this is not difficult on that, but it's a good counter example. That's why the separability doesn't behave that nicely. Okay, the open subspace it has to be, and I told you where open you need at that. Okay, but you should complete that proof. Okay, so that let me tell you that I won't teach you anything more on this subspace of that, but some subspace result will later come on. That I will do that of course, but right now I won't teach. So that tomorrow I will take the class, the Friday. I don't know what is the Friday date. What is the Friday? 17, 21.
21.
21, right? So I will take the class on Friday, and Friday I am going to teach you quotient space. Look, quotient space. Just let me tell you that if we are looking at Ali Francis, because this is also has good analytical things. In fact, next semester function analysis also will need that. So, but he has defined quotient topology in problem number 20, page 65. Okay, right. So that of course I will take the quotient topology. But Willard has done extensively. Reason is quotient space is also this very useful in the you need algebraic topology and differential topology. In fact, combination of this, a new thing is coming that is called geometric topology. It's called the geometric topology. When you link between, look here, differential topology, there is a branch that is actually differential topology, differential geometry. This is not the old style, new style of geometry is that you use always differential topology. So that differential geometry basically nowadays is another name of differential topology. Geometric topology is actually is a part of differential geometry, you can say that, but it also deals with something is part, but you do something other different thing also. Not only it is differential geometry. In fact, any topological problem where you involve geometry, then you have geometric topology. Let me tell you something. These days, because actually US dictates which field should be studied, because the technological, the number one country in the world, they always going to look for what will be the good for topology, and particularly computer science and that. So they figured out that geometry is the main thing you need. Geometry. So anything where you do for higher study, even for company job and that, unless you involve geometry, you may lag behind. So that they're always encouraging anything. You'll have to push geometry. Okay, so that's the differential geometry, geometric topology. All these are hot topic, even in the computer science also. Okay, that you should keep in mind, the geometry, because geometry in vision theory particularly is very important. In vision, in computer science, whatever geometry, it's not the give you great thing of deal of geometry, but you need geometry. That's why if you want to do something, you should something do related to geometry. Even in the function analysis, they always talk about geometry. Like this is an old topic, but now it is alive. Geometry of Banach spaces. Look, Hilbert space, that in linear algebra, I don't know who taught you. Geometry of Banach spaces, because in our product space, even for a higher dimensional, infinite dimensional, you can do geometry, because there you have the concept of the orthogonal elements. But how to do in the Banach spaces, there you may not have the concept of orthogonal elements. That's the geometry of Banach spaces is much more difficult, and people still try to do that. In fact, there's an area in Banach space, geometry of Banach space. That means geometry has to be there. Okay. So that's a good thing. Even if you go for higher studies, PhD, something geometry has to be there. When you go for a company job, somewhere geometry will have to be there. Okay. Now I want to tell you one more thing, that it is not exactly math, but some of you since submitted assignment, I want to tell you something in that. Because logically you should be sound in that also. Okay. So what is that? Here in logic, suppose you have a statement P. P implies Q. P is a statement, Q is a statement. That means if you assume P is true, then Q is true. It doesn't mean that P is true. But if you assume P is true, then Q is true. Okay, right? And here, when you write, suppose you have a, you know P is true. Suppose you know P is true. Suppose. And then you write, suppose then I have, suppose P is true, but P implies Q. So you get Q. Okay. So you get Q. Look, here you are only assuming P. But if you assume P, you know that then Q will be true. But here if you write let P implies Q, look, this is not the same statement. Here your whole assumption is that you assume P implies Q. Here your assumption is only P. Understand? Here actually let P. That means let us assume P is true. Okay, here, so these two, this is different from this. Here your whole thing you are assuming this, and here only you are assuming P. Some of you are given assignment, you are, that the students often they make mistake, they write that. Okay, so that be careful that what is your hypothesis, and after the hypothesis what you are getting. So this is the logical thing. P implies Q and let P implies Q, they are different. They are different. Here you are assuming the whole thing, let P implies Q. Here you actually have P, then Q is true. Okay, so that is one thing you should understand. Next thing is that what I want to teach you a little bit of English at that. Okay. You may wonder that being a mathematician, I am talking about English. Well, I have been always interested in language. Other than English, I know a little bit of other language, other than Hindi also. That is because I did PhD in the US. I had to take two languages, German and French. Okay. But eligibility in the department, I took the test in French, not German. Though I got in German A and here I got A minus in the language department. But then I learned Spanish on my own. Okay. In fact, my daughter who studied in the DPS, she took Spanish, her third language. So I used to teach her Spanish. So I have healthy interest in language and that. So let me tell you that in Hindi you will find it because Hindi is a product of Sanskrit, a daughter of Sanskrit. What you write, I'm writing the English, Mool Kriya. In English, they call it root verb. Okay. Look, Mool Kriya, root verb means the verb, it's got a form. From that, you get a different form depending on the sentence. Like, let me tell you that be is the root verb. From that, you get, depending on the tense. In Hindi, you can also find that. Like gaya, gai, gai, changing. But main thing is gaya. Okay, then the Mool Kriya. Be is this. Here is, am, are, was, were. These are different forms. Even be also. They are different form of this, but this is the root verb. Root verb. Okay. Similarly, look, you have these two forms: has, have, then had, the past tense. But root form is actually have. Root verb. So in the late, remember that in the word late, you must have always root verb. Like the do, I have did, done, have done, all this. So that let it be true. Or let us have. It is not has. I mean, let me have. Let us have. Even if you take 1%, let he have. Let he have. Not has. Okay, let it be. Because hey, I have is the root form. So in the late, in the mathematics, you often you assume late with the word starting with the late, it should be always be, have. Let us do it, not something else will come. Okay, so that with late is always root verb, which is in English, in Hindi or Sanskrit, you call it mool kriya. That means mool form of the original form of the verb. That may change with the person, with the tense, but that is called. So that don't forget it. Okay, this is important. Okay, you are writing that. Okay, so be careful. That I on the logic I told you that what is the difference between two statements and keep note of this. Okay, see you on Friday. Okay, bye.
Thank you, sir.
Okay.
Thank you, sir.
করো হলো এটা কোথার থেকে এলো? এটা কি করে এলো এটা?